All right, get ready for this. We're diving deep into the fascinating world of light and matter. We've got Chapter 5, Light and Matter, from Professor Ramesh Dungana's book, and we're ready to unpack it all.
Oh, this is going to be good. Light and matter, the very essence of the cosmos. Understanding how they interact, it really opens up the universe for us, doesn't it?
It totally does. I was reading about how light doesn't just travel through space, it interacts with matter. It's incredible. Emission, absorption, transmission, reflection. It's a whole cosmic dance.
A cosmic dance. Yeah, that's a great way to put it. It really is. Every time we look at a star or a nebula or even a distant galaxy, we're seeing this dance between light and matter playing out.
It's mind-blowing. And Professor Dogana's chapter, it jumps right in, starting with the nature of light itself, this idea that light is both a wave and a particle. It's just incredible.
It's called wave-particle duality, and it's one of the most fundamental concepts in physics. It's like light can be this wave, spreading out like ripples on a pond, but it can also act like a particle, this tiny packet of energy called a photon.
So which one is it? A wave or a particle? It's got to be one or the other,
Oh,
right?
that's the thing. It's both. That's what makes it so fascinating. It really depends on how we're observing it and the kind of interaction that's happening. Sometimes it makes more sense to think of light as a wave, and sometimes the particle model works better.
Okay, so how does this wave-particle duality actually play out in space? Like, what does it look like when light interacts with matter?
Well, let's take emission, for example. Emission is when matter releases energy as light. Think about stars. They're these giant balls of hot gas, and their atoms are constantly emitting photons, giving off light.
So every star we see is basically just blasting out streams of light particles.
You could say that, yeah. And the color of the light that's emitted, it depends on the energy of those photons. That's how we get all those amazing colors we see in nebulae and galaxies.
So what about absorption then? Is that like the opposite of emission?
Exactly. Absorption is when matter takes in energy from light. Imagine light passing through a cloud of gas, right? Some of those photons, they can get absorbed by the atoms in the gas, which boosts their energy levels.
So it's like a cosmic energy transfer. Light gives this boost to the matter it encounters.
Precisely. And this absorption process, it can actually tell us what the gas cloud is made of. Different elements absorb specific wavelengths of light, you see. So they leave behind these kind of fingerprints in the light that passes through.
That's incredible. It's like we can figure out the chemical makeup of a gas cloud just by looking at the light that went through it.
It's like cosmic detective work, right?
Totally. Okay, so we've got emission, we've got absorption. What about transmission?
Yes, transmission. That's when light passes through matter without being absorbed or scattered, like how we can see through glass.
Right, so some materials are just better at letting light pass through undisturbed.
Yeah.
And then there's reflection. That's how we see most things, right?
Absolutely. Reflection is when light bounces off a surface. When you look at a book, you're seeing light that's reflected off the pages. And the color of the book, well, that's determined by which wavelengths of light are reflected and which are absorbed.
Okay, so we've got emission, absorption, transmission, and reflection. It's like a whole toolkit of light-matter interactions. But how do these interactions help us understand the universe on a bigger scale?
Well, one really cool example is how these interactions create what we call the electromagnetic spectrum. Remember those photons we talked about? The little packets of light energy, they come in this huge range of energies, and that range makes up the electromagnetic spectrum.
Right, the spectrum from radio waves to gamma rays.
Yeah.
And visible light is just a tiny little sliver in between.
Exactly. And it's the processes of emission and absorption of photons by atoms, that's what creates this spectrum. By studying the different wavelengths of light that are emitted or absorbed by these objects out in space, we can learn a lot about their composition, their temperature, even their motion.
This is all starting to make sense. But you mentioned temperature. How can we possibly tell how hot a star is just by looking at its light?
That's where Wien's law comes in. Wien's law, it's a tool that relates the temperature of an object to the peak wavelength of light it emits. So hotter objects emit more energetic light, meaning shorter wavelengths, which peak in the bluer part of the spectrum. Cooler objects, they emit less energetic light, peaking at longer, redder wavelengths.
So a blue star is much hotter than a red star. It's like a cosmic thermometer.
You got it. Wien's law lets us figure out the surface temperatures of stars just by analyzing the light they give off. And that tells us a lot about their life cycle, their energy output, even what will eventually happen to them.
Wow. But you also mentioned motion. Can we really tell if a star is moving towards us or away from us just by its light?
We can, and we do this using the Doppler effect. You know how a siren sounds higher pitched when it's coming towards you and lower pitched when it's going away? It's the same idea. With light, the Doppler effect causes a shift in the wavelength of light emitted by a moving object.
So if a star is moving towards us, its light would be shifted towards the bluer end of the spectrum, and if it's moving away, it'd be shifted towards the red.
Exactly. We call this shift the Doppler shift. By measuring it, we can figure out the velocity of a star, or even a whole galaxy, relative to us here on Earth.
It's like a cosmic speed gun.
It's a good way to think about it.
So we've been talking about light as both a wave and a particle, right? But how does this Doppler effect work with both models? Does it affect the wave or the particle? Or both?
That's a great question, and it's one that has puzzled physicists for a long time. The answer is it affects both. It affects both the wave and the particle aspects of light. Think of it this way. When a light source is moving towards you, towards an observer, the waves, they get bunched up. You see, their wavelength gets shorter. It's kind of like a slinky, when you compress it. This is what causes that blue shift.
Okay, yeah, I can see that. Shorter wavelengths, higher frequency, bluer light. And then when the source moves away, the waves get stretched out. So that causes a redshift.
That's exactly it. Now, if we think about light as a stream of those photons, the Doppler effect, it's basically a change in the energy of those photons. So as the source moves towards the observer, each photon carries a little bit more energy, and that means a higher frequency, shorter wavelength. Again, a blue shift.
So whether we're thinking of it as waves being squeezed together or photons getting an energy boost, the result is the same. The color of the light shifts depending on how the source and the observer are moving relative to each other.
Exactly. And this principle, it's really changed how we understand the universe. By measuring those Doppler shifts of light from distant galaxies, we've discovered that the universe is expanding. It's amazing these galaxies are moving away from each other at incredible speeds.
It's like the whole universe is this giant balloon, and it's expanding, and the galaxies are like dots on the surface, getting farther apart as the balloon inflates.
That's a great analogy. And the Doppler effect is one of the key pieces of evidence that supports this whole idea of an expanding universe. But it's not just about galaxies moving apart, the Doppler effect. It helps us understand the motions of stars within galaxies, the way gas swirls around black holes, even those tiny wobbles of stars caused by planets orbiting them.
Wow, that's a pretty powerful tool then. It's like a decoder ring for the universe. It's showing us these hidden movements of everything out there in space. But you mentioned black holes. They're known for having this incredibly strong gravity, so strong that even light can't escape. So how does that fit in with this whole interaction of light and matter?
That is a great question. Black holes, they're kind of a unique and extreme example of how gravity can affect light. It's true, light can't escape from inside a black hole's event horizon, the point of no return. But the area around a black hole, it's a real hotbed of light-matter interactions.
So even though we can't see the black hole itself, we can see all this activity happening around it.
Exactly. The black hole's gravity, it's so strong, it pulls in gas and dust, and it forms this swirling disk of material. We call it an accretion disk. And as this material spirals inwards, it heats up because of friction and the gravitational forces, and it gets really hot, millions of degrees.
Like a cosmic whirlpool, the matter's getting superheated as it goes down the drain.
That's a great way to picture it. And all this superheated material, it emits intense radiation, including X-rays and gamma rays, and we can detect those with our telescopes.
So these black holes, these invisible monsters, they're actually some of the brightest objects in the universe because of all this activity, all this light they create as they're pulling in matter.
It's a bit of a paradox, isn't it? But even in these extreme environments, the basic principles of how light and matter interact, they still hold true. We see emission as the hot gas radiates energy, absorption as the gas absorbs some wavelengths of light, and even reflection as light bounces off that swirling disk of material.
It's like a cosmic lab. We're seeing light and matter interacting under the most extreme conditions we can imagine. But, we've been talking about how light interacts with matter. What about the other way around? Does matter affect light in any other ways besides just emitting, absorbing, transmitting, or reflecting it?
No, that's a really insightful question. And the answer is yes. Matter can actually bend light. We call this gravitational lensing, and it's a direct result of Einstein's theory of general relativity.
Gravitational lensing. Sounds like something straight out of science fiction. How does that work?
Well, imagine this. There's a massive object, like a cluster of galaxies, and it's sitting between us and a distant light source, like a quasar. The gravity of that galaxy cluster, it actually warps the fabric of space-time around it, and this warping, it bends the path of light coming from the quasar.
So it's like looking through a warped piece of glass. The light gets distorted, bent, as it passes through that gravitational field.
Exactly, and this bending, it can create multiple images of the quasar, or even arcs or rings of light. It's like the quasar's light is magnified and distorted by a cosmic lens.
It's using gravity to make a natural telescope, magnifying and distorting the light from these distant objects. But wait a minute.
What is it?
If gravity can bend light, does that mean light has mass? I thought it was supposed to be massless.
Another great question. That gets to the heart of how we understand gravity and the nature of light. The truth is, light doesn't have what we normally think of as rest mass. It's always moving, at the speed of light. But because light carries energy, and energy is equivalent to mass, according to Einstein's famous equation, E=mc², light kind of behaves as if it does have mass when it interacts with gravity.
So light is massless, like it doesn't have any inherent mass when it's at rest, but it acts as if it has mass because of the energy it carries. That's kind of tricky.
It is. It's a subtle but really important distinction. And this strange behavior of light, it really impacts how we understand the universe. Like with gravitational lensing, it lets us study dark matter, that invisible form of matter that doesn't interact with light except through gravity.
So we're using the way light bends around these galaxy clusters to map out the dark matter that's holding them together. Wow.
It's pretty amazing, yeah.
But we've been focusing on how light interacts with matter out in space, but it's also the basis for so much technology we use here on Earth.
You're absolutely right. Our understanding of light-matter interactions, it's led to so many advancements. Lasers, fiber optics, solar panels, digital cameras. The list goes on.
It's really incredible how something as fundamental as the interaction of light and matter can have such a huge impact on our lives, both in understanding the universe and in all the technology we use every day.
It's pretty remarkable.
This deep dive, it's been a real eye-opener. Seeing how this intricate dance between light and matter plays out on such a massive scale, and right here in our everyday lives.
And as we keep exploring and experimenting, who knows what other amazing things we'll discover about light and matter. I think the universe is full of secrets just waiting to be revealed. And light is the key to unlocking their secrets.
It really makes you think. Every time we look up at the night sky, we're not just seeing points of light, we're seeing billions of years of cosmic evolution driven by the interaction of light and matter.
Absolutely. It's a truly humbling and inspiring thought.
This deep dive has been incredible. It's really opened my eyes to the complexity and beauty of the universe. Thanks for sharing your expertise and guiding us through this exploration of light and matter.
It's been my pleasure. And remember, the universe is like a book written in the language of light, and it's up to us to learn to read it.